Welcome to this explainer, where we're going to map out the absolutely fascinating architectural journey of human development, and of course, the profound maternal adaptations that actually make the whole shebang possible. Think of this as a story of incredible precision. We've got millions of cells orchestrating this complex biological dance to build a life, while at the exact same time, an entire physiological support system shifts into high gear to protect it.
So let's kick things off with a pretty wild question. We often take the outcome completely for granted, but how exactly does a simple microscopic cluster of cells transform into a highly complex, fully functioning human being? Like, how does the body build a human from scratch? And just as importantly, what happens when that highly choreographed blueprint gets interrupted? Today, we're going to look closely at this process, step by step, and really explore the remarkable resilience and the specific vulnerabilities involved along the way.
We're going to follow a structured blueprint today. 1. The two-layered start. 2. The germ layer shuffle. 3. The origins of our organ systems. 4. Maternal body adaptations. And finally, 5. Those critical windows of vulnerability.
All right, part 1, the two-layered start. Let's dive right into week 2 of gestation.
Right after implantation, the inner cell mass differentiates into a bilaminar disc. Now, a super easy way to remember this split is this. The epiblast makes the embryo, while the hypoblast just says hi and bye. Basically, the dorsal columnar cells form the epiblast, which is literally the source of all future germ layers. The ventral cuboidal cells, well, those form the hypoblast, which eventually gets completely displaced and doesn't even contribute to the final embryo. So yeah, it truly just says hi and bye.
Moving on to part 2, the germ layer shuffle, which happens during week 3 gastrulation.
Okay, so this is where things get truly dynamic. Gastrulation kicks off with the formation of the primitive streak. I want you to think of this streak as the architectural starting line. It completely sets the entire body's cranial, caudal, or head-to-tail axis. Those epiblast cells we just talked about, they actually begin to migrate inward or invaginate right through this streak to create our 3 primary germ layers, the ectoderm, mesoderm, and endoderm. Memorizing the origins of our organs is actually a breeze if you use a few memory hooks. First up is the ectoderm, or as I like to call it, the attractoderm. This forms the things that attract you to others on the outside, like the epidermis of the skin, your hair and your nails, plus your entire nervous system. Next is the mesoderm, the mesoderm. This represents your means of getting things done. We're talking muscles, bones, the heart, and your kidneys. Finally, the endoderm, or endoderm. This one forms your internal organ linings, giving rise to the gastrointestinal tract epithelium, the liver, and the lungs.
All right, part 3, origins of organ systems, or how we go about building complex structures.
You see, it isn't enough to just have 3 flat layers of cells. They have to interact. Let's look at the central nervous system. This incredible step-by-step biological folding process is called neurulation, and it's entirely driven by the notochord. Now, the notochord is a structure derived from the mesoderm, and it acts as the master inductor. It essentially sends signals to the overlying ectoderm, telling it to thicken into a neural plate. The center of this plate dips down to form a neural groove, and the lateral edges rise up as neural folds. Eventually, these folds approach the midline and fuse together to create the neural tube. And that tube is the direct precursor to your brain and spinal cord. And this precise folding sequence is exactly why folic acid is absolutely critical in early pregnancy. If that highly orchestrated fusion process fails, which typically happens right around the 4th week, it leads to open neural tube defects. For instance, if the caudal neuropore fails to close, you get conditions like spina bifida, specifically myelomeningeal, where the spinal cord and its protective meninges are actually exposed outside the body.
But get this, even within a single layer like the ectoderm, distinct developmental paths emerge. The general surface ectoderm forms our outer coverings, so epidermis, hair, and nails. But a specialized subpopulation called the neural crest actually migrates extensively throughout the entire embryo. These neural crest cells give rise to melanocytes in our skin and Schwann cells in our nervous system. This developmental origin is incredibly relevant clinically. Why? Because it means that melanoma, a really dangerous skin cancer, is fundamentally a disease of neural crest origin.
Now for part 4, maternal body adaptations. This is all about the systemic support required to make this happen.
Constructing this embryological blueprint requires massive systemic support. The fetus cannot build itself in isolation. Because of that, the maternal body undergoes a complete structural and metabolic overhaul.
Normally, in a non-pregnant state, insulin and fat metabolism operate normally to store energy. But during pregnancy, the maternal body transitions into a state of progressive insulin resistance and increased lipolysis, which is just the breakdown of fats. This happens so the mother's body relies more on fat for her own energy, which ensures the growing fetus gets the easily accessible glucose energy it so desperately needs.
Interestingly enough, despite that state of insulin resistance, maternal fasting glucose levels don't actually spike. They drop by 10 to 20%. So why is that? Well, it's because the developing fetus acts as a constant, heavy drain on the mother's glucose reserves. The maternal system is essentially rerouting its prime energy supply directly to the baby 24/7. And glucose definitely isn't the only resource being diverted in massive quantities. The sheer metabolic demand for building a skeleton is honestly staggering. To put it into perspective, by the third trimester, the fetus is extracting 200 milligrams of calcium every single day from the maternal supply just to mineralize its growing bones. To protect this highly demanding, developing life, the maternal body also generates a really robust protective cushion. By term, the maternal and fetal systems collaborate to maintain an amniotic fluid volume of 800 to 1,000 milliliters. That's about a whole liter of fluid. This fluid provides a vital physical buffer, allows for fetal movement, and most importantly, protects all that delicate architectural work happening inside.
This brings us to part 5, windows of vulnerability. What happens when the blueprint fails?
So what exactly happens when external factors interfere with this highly orchestrated blueprint? Well, as resilient as the developmental process is, there are specific windows where it is profoundly fragile. We have to look closely at teratogens. These are essentially agents, like certain medications, that interfere with normal fetal development, either by disrupting cell proliferation or just being outright toxic to developing tissues. Teratogens can cause devastating disruptions, but what's essential to understand here is that their exact clinical impact depends heavily on the specific timing of the exposure relative to gestational age. This timeline clearly maps out our critical windows of vulnerability. If an exposure happens in the first 2 weeks, the pre-implantation phase, it's generally an all-or-none effect. Basically, the embryo either fails to survive or it survives completely unaffected. However, weeks 3 through 8, that's the period of organogenesis. This is when those germ layers are shuffling and organs are actively folding into place. So exposure to teratogens during this specific window carries a massive risk for severe structural malformations.
But even without external teratogens, when normal embryological fusion is disrupted, we see some fascinating but highly problematic structural anomalies. Take the horseshoe kidney, for example. In this case, the lower poles of the developing kidneys mistakenly fuse together. As they try to move up to their normal position in the abdomen, this fused U-shape gets trapped right under the inferior mesenteric artery. This leaves the kidneys sitting much lower in the body and prone to blockages. Similarly, if the ventral and dorsal buds of the developing pancreas fail to completely fuse together, you get a condition called pancreas divisum, where 2 separate ductal systems persist.
All of this leaves us with a final thought to ponder. Given the remarkable resilience yet profound fragility of early human development, from the precise signaling of the notochord to the immense metabolic adaptations of the mother, how can medicine continue to better safeguard this miraculous process? Understanding this chronological blueprint isn't just about memorizing facts, it's the absolute key to protecting the very foundations of human health.